All right. So in the last lecture, if you recall, we raised a question that how is it possible that if we approach আচ্ছা তোমরা দেখতে পাচ্ছ? Can you see the screen?
Yes, sir.
Okay. And his voice is okay?
Yes,
Yes, sir.
So in the last lecture, raised a question that we have different approaches to deal with a system. However, two approaches are totally different. Even then, how come the results that similar? So that's the question we posed, and we actually were in the quest of the answer to that question. And eventually for that we did look at the energy fluctuation in the canonical ensemble, and we went through all these things in the earlier classes. We looked at the fluctuation, relative fluctuation in energy, and that goes as inverse of root n. And of course, when we are talking about the statistical system, the thermodynamic limit. In the thermodynamic limit, we get a reasonable result, and therefore n tends to large, and hence the relative fluctuation is so can I make the volume a little less? Okay. So আসলে কানে লাগছে। আচ্ছা শুনতে পাচ্ছ তোমরা? আমি একটু কমিয়ে দিলাম কানে লাগছে বলে। হ্যালো?
হ্যাঁ, শুনতে পাচ্ছি।
So okay, all right. So as n is very large, and therefore the relative fluctuation tends to zero, and it implies that most of the energy is which is responsible for contributing the system is the average energy, as the fluctuation on that is tending to zero large system, and that is the key for which we get the same result. Either we approach the microcanonical ensemble procedure, or we adopt the canonical approach. Okay, so whatever, again, we had seen through detailed calculations in terms of probability, when the probability is maximum, at which energy the probability is maximum, that turned out to be the average energy. Then we did expand the probability, and it turned out to be eventually a Gaussian distribution type. And for large number of particles, again, we found that that distribution approaches a delta function, that is the fluctuation around the energy, average energy is very little. And finally, we took a specific example of classical gas, non-interacting gas, and there we found that average this energy at which the probability is maximum is 3n by 2 minus 1 kt. If n is large, then we can neglect this minus 1, and therefore it is like a drop in an ocean that we can always neglect. 3n by 2 is a large number compared to 1 you can neglect, and therefore it turns out to be 3n by 2 kt, which is of course the average energy of the classical gas that we have seen many times earlier. And therefore it again confirms that the relative fluctuation, that the peak that happens, probability peak happens at the average energy, and it takes a shape of delta function, and therefore the relative fluctuation tends to zero. From that, we looked at the partition function. Partition function is this, because in terms of probability you can write the partition function, and it turns out to be like this integration you can evaluate this integration, the result with pi, and therefore it turns out to be like this. And then if you take the log and multiply minus kt to get a, it turns out to be like this within this term, and for large number, because this is proportional to and the number of particles, and this is ln of n. As a result, this term is negligible compared to this, and eventually you obtain this result. Again, the similar kind of result as you obtain in case of microcanonical ensemble also. Well, given that, let us, as I said, that you will be never satisfied if you are very critical about something, to accept something new, and which coincides with earlier one. So you should be more critical, and then you wish to have more proof that both the results give the both approaches produces the similar kind of results, and that's why we have, in the microcanonical ensemble, we did calculate the expectation value of this xi h del h del xj. So have you seen this? I told you to go through this before the class. So did you?
Yes, sir.
Or did you understand that?
হ্যাঁ, বুঝতে পেরেছি।
Okay, all right. So and this is Mosumi, and how about others?
হ্যাঁ স্যার দেখেছি।
Okay, who is speaking?
সোমাশ্রী স্যার।
So did you understand that?
হ্যাঁ স্যার ঠিক আছে।
Okay, all right. Abhishek?
হ্যাঁ স্যার।
So Abhishek, can you explain this to us? Then I'll be benefited in a sense that I'll come to know that you have understood it, and second benefit that your friends will listen to you. Can you do that? Can you present it? You take my note and then you just
না স্যার, ঠিক এক্সপ্লেইন করতে পারবো না, একটু দেখতে হতো।
Okay. So Samasri, can you do that?
স্যার একটু দেখতে হবে, দেখছি একটু।
Okay. Moshami, how about you?
স্যার ক্যালকুলেশনটা তো?
Hmm?
হ্যাঁ, বলতে পারবো।
Present it right now.
মানে
তুমি আমার
প্রেজেন্ট
নোটটা নিতে পারো, আমার নোটটা নিয়ে প্রেজেন্ট করো।
হ্যাঁ, একটু পরের পেজে যান তাহলে একটু।
পরে পেজে
পরে
যাব।
হ্যাঁ।
হ্যাঁ।
বলছি এখানে মানে প্রথমে যেটা আমাদের আপনি টার্মটা নিলেন, ওই উপরে যেটা ছিল টার্মটা নমিনেটরে, সেখান থেকে নিলেন হচ্ছে ইন্টিগ্রেশন ওভার।
হ্যাঁ, বলে এই জায়গা থেকে, তাই তো?
হ্যাঁ,
এই জায়গা থেকে এই জায়গাটা তুমি নিচ্ছ, নিউমারেটর টার্মটা এখানে নিচ্ছ, তাই তো?
হ্যাঁ, সেই টার্মটা আগে নিলাম। এবার সেই টার্মটাকে আগে করলেন আপনি, মানে কি হলো সেটাকে মানে করছিলেন অনেক
না, এই টার্মটাকে আমি এখানে একটু গুছিয়ে নিয়েছি। এই
হ্যাঁ,
টার্মটা
ওটাই বলতে
দিস ইজ দ্য
গুছিয়ে
সেম
নিয়ে
টার্ম। হ্যাঁ হ্যাঁ, এটা
হচ্ছে যেটা কি xi, এই যে সেকেন্ড লাইনটা লিখেছেন xi অফ -1/β del x del xj অফ e টু দি পাওয়ার মাইনাস অফ বিটা এইচ। এবার এই টার্মটা করতে গেলে লাইনটা পাচ্ছি, কারণ আমরা জাস্ট এখানে ওই ডেরিভেটিভটাই করছি। ডেরিভেটিভটা করলে -1/β আছে, দিয়ে কেটে যাচ্ছে। পরের লাইনটাতে যখন যাচ্ছি তখন আমরা হচ্ছে ওই সেম লাইনটাকে লিখেছি, জাস্ট ব্র্যাকেটটাকে করে, আর কিছু না। আর 1/βটাকে বাইরে নিয়েছি, মানে রিঅ্যারেঞ্জ করেছি, আর কিছু না। আর তারপরে এই যেটা ইন্টিগ্রেশনের ভিতরে টার্মটা আছে সেটাকে লিখেছি এখানে, আর দিয়ে ওটাকে আরো রিঅ্যারেঞ্জ করেছি। তো সেখানে করেছি হচ্ছে প্রথমে এখানে জাস্ট ছিল হচ্ছে ডেল ডেল xj অফ e টু দি পাওয়ার মাইনাস অফ বিটা এইচ। এবার আমরা টোটাল মানে xj-টাকেও ভিতরে ঢুকিয়ে দিয়ে টোটালটা ডেল ডেল xj নিয়েছি। এবার সেটা করতে গেলে আরেকটা টার্ম বিয়োগ দিতে হবে। এবার যেহেতু মাইনাস বিটা ছিল তাই সেটা প্লাস অফ বিটা হলো, আর দিয়ে হ্যাঁ, এই প্লাস অফ বিটা হলো e টু দি পাওয়ার মাইনাস অফ বিটা এইচ বের হয়ে গেল। আর দিয়ে হচ্ছে এবার ইন্টিগ্রাল ডেরিভেটিভটা আছে সেটা হবে হচ্ছে xi এর উপর। তো ডেল অফ x ডেল অফ xj থাকলো, আর দিয়ে আবার ওই সেই টার্ম ডেল 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 x হয়।
তাহলে এইটা এখানে ইন্টিগ্রেশন হচ্ছে, এই টার্মটার এই টার্মটার।
হ্যাঁ, এখানে এই দুটো টার্মকে বসিয়ে দিলেন, দিয়ে প্রথম টার্মটা 0 হলো। তার কারণ হচ্ছে ওই এক্সট্রিম ভ্যালু গুলোতে এই এইচ এর ভ্যালুটা হাই হয়, তার জন্য হচ্ছে e টু দি পাওয়ার মাইনাস বিটাটা 0 এর দিকে টেন্ড করবে বলে ওই জিরো হয়ে যাবে, দিয়ে সেকেন্ড
কিন্তু
টার্মটাই
এইটা
বেশি।
পড়ে থাকবে। হুম।
হ্যাঁ, second termটা পড়ে থাকবে, দিয়ে এই সেকেন্ড টার্মটাকে তো
এই
ডেল্টা।
টার্মটা মানে এই টার্মটা মানে এইটা এইটা
হ্যাঁ
এইটা এইটা, হ্যাঁ এইটা।
হ্যাঁ, এবার এই টার্মটাকে তো ডেল এক্স আই ডেল এক্স জেটাকে তো ডেল্টা আই জে লেখাই যেতেই পারে। এবার
কেটে
সেটাকে
আছে,
লিখে
হ্যাঁ
দিলে
এই যে এইটা।
ডিনোমিনেটর আর ন্যুমারেটরটা
হুম
সেম হয়ে যাবে। দিয়ে ওই
হুম
দুটোকে কেটে জাস্ট ওয়ান বাই বিটা কেটি পড়ে, সরি ওয়ান বাই বিটা ডেল ডেল আই ডেল যেটা পড়ে থাকছে, ডেল আই যেটা পড়ে থাকছে, দিয়ে ওয়ান
হুম
বাই বিটাটাকে কেটে বসেছি।
হুম। সো দিস ইজ দিস। এবার সবাই বুঝতে পারলে? নন্দিনী, নন্দিনী, নন্দিনী আছে
হ্যাঁ
না
স্যার।
নেই আছে? বুঝতে পেরেছো?
হ্যাঁ
হ্যাঁ
হ্যাঁ স্যার, বুঝতে পেরেছি।
আচ্ছা, অভিনন্দা?
হ্যাঁ স্যার, আগেই বুঝেছি।
তোমার
হ্যালো
এত
স্যার।
নয়েজ হচ্ছে কেন তো
স্যার আমি
বাড়িতে?
বাস বাস স্ট্যান্ডে আছি।
ও
আমি বোলপুরে এসেছিলাম, বাড়ি ফিরছি, ওই জন্য বাস স্ট্যান্ডেই আছি। আওয়াজ হচ্ছে।
ও, বোলপুর কেন এসেছিলে?
স্যার ওই ইন্সপায়ারের ওই সাইন করানোর জন্য।
ও আচ্ছা আচ্ছা আচ্ছা, কি ডিপার্টমেন্টে?
হ্যাঁ হ্যাঁ, ডিপার্টমেন্টে এসেছিলাম।
ও, কে তাপসদা সাইন করলো নাকি?
হ্যাঁ হ্যাঁ, তারপর তো সাইন করেছি।
আচ্ছা আচ্ছা আচ্ছা, ওকে অলরাইট, ঠিক আছে। হোপফুলি তোমরা বুঝেছো, মৌসুমী সুন্দরভাবে এক্সপ্লেন করলো যে এই টার্মটাকে নিয়ে নিউমারেটরটাকে নিয়ে একটু ট্রিকি ওয়েতে লিখেছো আর কি। As Mosumi said, that this you wrote a xi because you are doing the integration over xj, right? So xi is like constant. So you keep aside xi and then you can write this, because if you take the derivative, then del h del xj will come, e to the minus beta j. So this will come. So that is what, as she said, that just you have taken this inside. That's all you have done. And beta minus 1 by beta you have kept outside. That's all you have done. Again, from this term, 1 by minus beta, then xi del xj del beta, that you can write it as whole derivative of this. And then you have to subtract the one you have taken extra here. That you have done there. And as a result, you get this. And then this is your, this one, right? So if you put it here, this term, if you put it here, then that is, you have to integrate over this, right? And that is what you have done here. You have done the integration over this. So this one del xj, you are doing over xj, and therefore this term will come out, and then your limiting value, the extreme values. And then this one, 1 by beta, e to the minus beta h del I del x del xi del xj, and then if you are integrating over. And this is delta ij, and this will be 0, as Masumi said. And this, you know, xi, xi, xj, and this d omega prime, you remember, we mentioned it earlier, because d omega is the product of dx1, dx2, dx3, everything, right? So this is the elementary volume, you know, without the jth coordinate, jth element, right? If you now take a product this, then again it will, you know, it will go back to the original d omega, right? And that is what you have done here, that 1 by beta, this one 1 by beta delta ij, and this is it by beta h, and if you multiply these two, this will give you d omega. So this is what it is. Delta ij you take out, delta ij by beta, and then this is the same, and then it cancels out. So delta ij kt. So basically, if I equals to j, then the average value is the kt, and that is what we have written here. You see the equipartition theorem, that is sum over I equals to 1 to 3n. If you have 3n, you know, coordinates in the in the uh, you have yeah, you have three n number of pi's would be there, and therefore if you take the sum over, then the pi del h del pi, that will give you pi qi dot, and this is 3n kt, right? Because every, you know, each term average will give you kt, both are I, so this is 3n kt, and h, you know, for free gas, free particles, pi square by twice m, and pi del pi h pi equals pi this equals to pi 2 pi square by m. So this is twice h, right? So pi del h del pi is basically twice of pi square by 2m, And then if you take the sum over this, then it will be twice h, and hence h would be half of this, and then Tn by 2 kt. And that is what, again, your known result, right? This is the energy, average energy of n free particles, or n free particles. It's a classical gas of n non-interacting particles, or n free particles. Each quadratic term in Hamiltonian corresponds to an energy of half kt. And that is what you say equipartition theorem. That is what you obtained in microcanonical ensemble, which I did, do explicitly, even though it was not a very trivial one, but we did it explicitly, right? If you remember correctly. And then let us do a one calculation exactly. Say, let's say for the free particle, this is the kind of kind of theoretical approach, that if the Hamiltonian is given, then they will have like this. But now let us take a Hamiltonian. So U average is in the canonical ensemble h e to the minus beta h dq d3n dp 3 p, and then this is known. And then you explicitly put the Hamiltonian sum over pi square by twice m, and then it will minus beta h of course again sum over pi square by twice m, and this the elementary volume in phase space, in the real space and momentum space, and then this is kind of your partition function type denominator. And then it is you can write in a tricky way, and this trick is very often used in statistical mechanics. Okay, so try to remember this, because you may recall this kind of trick in various places in statistical mechanics. When you work out some problem, you need this trick, del del beta minus del del beta ln of this. So basically what is this actually? What is this? Oh, okay. So integration, because your integration is over p and q, right? But in the exponential term, you have only p, and you are left q aside, right? So you keep q aside. Here also you keep q aside. So you are left with the p integration here and the p integration here. So only the p integration you can write in this form. You see, if you do minus del del beta ln of this, then it will be 1 by integration this, and then if you do del del beta, then sum over pi square by twice m, which is h, and that will be the h average, right? This is a tricky way of writing this. Now it will be easier to do the calculations. Minus del del beta. Now this and this cancels, because this is independent of p. So this cancels, the physical volume, total volume cancels, and you are left with minus del del beta ln of integration into minus beta h, right? H is this, and d3 and p. Now you see, if you expand this exponential argument of the exponential, basically we'll have similar kind of integration 3n times, right? And therefore you can write it, and each integration will give you spit out the same value, right? It does not matter what variable you take. If the integral form is same, then it will spit out, and the limits are same, then it will spit out the same value, right? And therefore you can write a single integration a to minus beta p square by twice m dp, and you then take to the power of 3n. Okay, so ln of this and ln, if you take the ln on this, then 3n will come out. So and you can do explicitly this integration in terms of gamma integration. You have done many times. If you do this gamma integration, then you can
বলছি লাস্ট লাইনটা আরেকবার বলুন তো, 3n টা টু দি পাওয়ারে যে দিলেন ওটা।
Oh yeah, basically you see what you do, I tell you that you don't take 3n. Okay, let's just take 3. Okay, for example, let's say let's take n equals to 1, right? Then you will have minus del del beta ln of integration to minus beta, then p1 square by 2m plus p2 square by twice m plus p3 square by twice m, and this is dp1, dp2, and dp3. Okay, you write that. Then you see, you can separate the integrations within the log, the minus del del beta ln of, then take the square bracket, and then write integration e to the minus beta p1 square by twice m dp1, then integration e to the minus beta p2 square by twice m dp2, then integration e to the minus beta p3 square by twice m dp3, because p1, p2, p3 are independent, right? So you can have each integrations. Now e to the power minus beta p square by twice m dp, if you do the integration, or rather integration e to the minus beta p1 square by twice m dp1, the integration value that you will get is same as e to the power minus beta p2 square by twice m dp2, right? And also you will get the same value for integration e to the minus beta p3 square by twice m into dp3, right? dp3, right? So only the variable names are different, but the forms are exactly same. Then if you, since you will have the same value for each three integration, you can write a simple integration e to the minus beta p square by twice m dp, and then you take the power 3, right? Did you get most of it? Did you get my point?
না স্যার ঠিকঠাক বুঝতে পারলাম না, মানে ক্যালকুলেশনটা কি করে ওটা থেকে ওটাতে আসছে।
Okay, all right. You take pen and paper, okay? So carry on with me, okay? Take pen and paper, and those who did not understand, please take pen and paper with you, okay? Now write minus del beta ln then you take a square bracket, okay? Open a square bracket and write integration integration e to the power minus beta sum over I equals to 1 to 3. I am making it simple, okay? And then we'll generalize. I equals to 1 to 3 pi square by twice m dqp square bracket close. Have you done that?
হ্যাঁ স্যার।
Okay. Now next line, minus del beta ln of square bracket open, or you make curly bracket, okay? Make a curly bracket, okay? And then open square bracket e to the power minus beta into, you take a first bracket, p1 square by twice m plus p2 square by twice m plus p3 square by twice m. And have you written Mosumi?
হ্যাঁ স্যার লিখছি।
Okay, okay. বলে বলবে।
হ্যাঁ হয়ে গেছে।
Okay. Or otherwise you can write p1 টা তুমি px ও লিখতে পারো, px square plus py square, I think that's better, px square plus py square plus pz square, এরকম ভাবেই লেখো। আর এই d3p টা তুমি লেখো dpx dpy dpz।
হ্যাঁ করলাম।
হলো?
হ্যাঁ।
Okay. Now again next line, minus del beta ln of curly bracket, then within first square bracket তুমি লেখো integration e to the power minus beta px square by twice m dpx। কার্লি ব্র্যাকেট, প্রথম কার্লি ব্র্যাকেট হবে, তারপর স্কয়ার ব্র্যাকেটের মধ্যে থাকবে e to the power minus beta px square by twice m dpx into, আবার স্কয়ার ব্র্যাকেট ওপেন করো, e to the power minus beta py square by 2m dpy, and then again open the square bracket, e to the power minus beta pz square by twice m dpz, square bracket close, curly bracket close.
হ্যাঁ করেছি।
এবার তুমি বলো আমাকে, ওই যে কার্লি ব্র্যাকেটের মধ্যে তিনখানা ইন্টিগ্রেশন আছে, তিনটে ইন্টিগ্রেশনই তো একই ভ্যালু দেবে নাকি?
হ্যাঁ।
Then I can write a single integration power to the power n.
হ্যাঁ।
That is what I'm doing here.
ওকে।
Okay, all right. So now you tell me what will be the value of this integration e to the power minus beta p square by twice m dp. Tell me the value of this, just this integration.
root over 2m pi by beta.
I don't know. I have not done it here. So root over, what you said?
Root over 2m pi by beta.
root over 2m pi by beta. এক মিনিট দাও তো, আমাকে একটু খাতা পেন আনতে দাও একটু। তোমরাও করো সঙ্গে। আমি হয়তো রাফে করে রেখেছি, বাট ইট ইজ নট উইথ মি in the note. So basically, let me see. Saying. So it will be a minus 3n. If I take the log of that, then it will be minus 3n del beta of the ln of integration e to the power minus beta p square by twice m dp, right? Okay, so it will be equals to minus 3n del beta of ln of integration টা ভ্যালু কত বললে তুমি?
Root over 2 pi m by beta.
root over 2 pi m by beta. Okay, then square root টার্ম আসছে তো, হাফটাকে বার করে নিয়ে চলে আসি, তাহলে মাইনাস 3/2n del beta of ln of twice pi m by beta, right? আচ্ছা, ওইটা del beta করলে কত হচ্ছে, করো পুরোটা। minus 3n/2 1 by ln মানে হচ্ছে 1 by 2 pi m উপরে বেটা, and then del beta of 2 pi m by beta কত হচ্ছে, minus 3n/2 into ওইটা কেটে যাবে minus 1 by beta, মানে 3/2 n কেটে। হ্যাঁ হচ্ছে। Did you do the calculation? All of you, did you do the calculation?
Yes, sir.
Others, how about others? Nandini?
হ্যাঁ স্যার হয়েছে।
আচ্ছা, সমাশ্রী?
হ্যাঁ স্যার, রুট ওভার এম পাই বাই টুয়াইস বিটা আসছে।
root over, হ্যাঁ, এবার log, if you take the log of that,
হ্যাঁ
then you
হ্যাঁ
can
হ্যাঁ
take half
হ্যাঁ হ্যাঁ
outside, right?
হ্যাঁ হ্যাঁ হ্যাঁ
And then do the del beta and eventually see whether it is coming at 3n/2 kbt or not.
হুম, ঠিক আছে।
Please do everybody and let me know once you are done.
স্যার হ্যালো
Hello?
স্যার, ইন্টিগ্রেশনটা কি বলছিলেন আরেকবার বলবেন? আমি ঠিক শুনতে পাইনি।
হ্যাঁ, ইন্টিগ্রেশনটা যেটা অভিনন্দা, আমার মনে হয় তুমি না বাড়ি গিয়ে আমাকে কল করো, ওকে? তুমি এই বাস স্ট্যান্ডের মধ্যে তুমি বুঝতে পারবে না এখন। হ্যাঁ
ওকে স্যার, ওকে স্যার।
হ্যাঁ হ্যাঁ হ্যাঁ। অনন্যা?
হ্যাঁ স্যার।
হয়েছে?
হ্যাঁ স্যার করছি।
আচ্ছা, অঙ্কিতা? হাউ অ্যাবাউট অঙ্কিতা?
হ্যাঁ স্যার করছি স্যার।
অর্ঘ, ডু ইট।
হ্যাঁ স্যার করছি।
হয়ে গেলে আমাকে বলবে, ওকে? দেন আইল প্রসিড।
স্যার আসছে।
কে ইমতিয়াজ? কে বললে ইমতিয়াজ?
হ্যাঁ স্যার, হ্যাঁ স্যার, ইয়েরটা বললাম, ওইটা আর একটু করি, পুরোটা হয়ে যাবে।
হুম।
স্যার হয়েছে।
কে গো?
স্যার দিব্যেন্দু।
দীপেন্দু, ওকে, গুড গুড গুড। আচ্ছা দিব্যেন্দু, তুমি একসময় একটা প্রবলেম দিয়েছিলে, হ্যাঁ, সেই প্রবলেমটা এখন কি ট্রাই করে দেখেছো? আমি যদিও ভুলে গেছি প্রবলেমটা।
ওই স্যার প্রবাবিলিটিটা তো দিয়েছিলাম যেটা।
হ্যাঁ
হ্যাঁ স্যার ওইটা হয়েছে।
হয়েছে। ক্যানোনিক্যাল দিয়ে করলে তো?
হ্যাঁ স্যার, হ্যাঁ স্যার ওই স্যার হয়তো ক্যানোনিক্যালটা ছিল না, অন্য একটা স্যার প্রবলেম ছিল, আগে দিয়েছিলাম ওইটা, প্রবাবিলিটি
অনেক
ছিল
আগে
স্যার ওই।
দেখি।
হ্যাঁ স্যার।
না, সেটার মধ্যে স্ট্যাটিস্টিক্যাল কি ছিল? স্ট্যাটিস্টিক্যাল কি ছিল?
স্ট্যাটিস্টিক্যাল ছিল না স্যার, প্রবাবিলিটির যে পার্টটা পড়িয়েছিলেন না ওই পার্টটার থেকে স্যার ছিল ফার্স্টে একদম।
তাই?
হ্যাঁ স্যার।
ঠিক আছে, আমি আবার দেখবো তোমার প্রবলেমটা, অনেকদিন আগে তুমি দিয়েছিলে আমাকে। তুমি করে ফেলেছো অঙ্কটা? দিবেন্দু?
হ্যাঁ হ্যাঁ স্যার, হ্যাঁ স্যার।
হয়েছে? হুম।
হ্যাঁ হয়ে গেছে।
আচ্ছা, আদার্স?
হ্যাঁ স্যার হয়ে
হ্যাঁ
গেছে।
স্যার হয়েছে। হ্যাঁ স্যার হয়ে গেছে।
Okay, all right, very good. Okay, so let's proceed. Okay, so then now let us consider another system. I mean, now we take this approach, canonical approach, and study some systems. And you know, a very important system for us, or very popular system, you know, in physics, basically, that we try to take an example. A system of n practically independent harmonic oscillators. Okay, so this study will tell us about the canonical ensemble formulation. You see, if it is harmonic oscillators, definitely each harmonic oscillator will have some coordinate, a pair of coordinates qi and pi. Qi is the, you understand, is the coordinate, spatial coordinate, pi is the momentum coordinate, and therefore h would be sum over, h would be for the ith oscillator, this h should be pi square by twice m plus half m omega square qi square, and these are very standard notation, mass and frequency of the oscillator. Okay, Now all oscillators are independent. Just mind it. All oscillators are independent. Okay. And the partition function of n oscillators should be the product of that of each individual oscillator, right? Because all oscillators are independent, as it happened in case of, as I just showed you earlier. Since they are all independent and their coordinates are independent, and you had that power, some integral raised power. Similarly here also, all these, since all these particles are independent, all these oscillators are independent, and therefore you can have a single particle partition function, and then probably you can have the product of them. Okay. For if you have n particles, you can have the n times of, n times product of that. Now you see, Q1, the single particle partition function, of course, this in 1D case, it is a two-dimensional phase space, and you know that each amount of volume corresponds to one microstate, one state, and the possibility is e to the power minus beta p square by twice m plus half m omega square q square. State possibility, that rho density of states, and that the probability that you talk about in canonical approach, e to the power minus beta h is this, and dq dp. Okay, and that turns out to be, if you do the integration, these integrations are very simple, right? These are Gaussian kind of integrations. So this one, as you said earlier, twice pi m by beta. If you have the p integration, and it's a q integration, that twice pi by beta m omega square whole to the power half. And if you have the product, is beta 1 by beta h cut omega. Okay, you do these things by yourself once, in pen and paper. Okay, so I know that you will not do it at home. Many times you keep it aside and you keep it for future. So and since these oscillators, you have n oscillators in the system, and each oscillator is independent with each other, and therefore you can have, or you can calculate the partition function for a single harmonic oscillator, and then you can raise the power. If you have n oscillators, if you can raise the power to n to get the partition function for n such harmonic oscillators. Okay, so please do this right now. This is the partition function for single particle. You divide by h, the phase space volume, to get the number of states, in a small elementary volume, and then you have the probability, and then if you integrate over, you get the partition function for a single particle state. Do this integration.
স্যার এখন
Get this
করতে
done.
বললেন?
Yes,
ওকে,
do it right now. Very simple, do it right now.
স্যার হয়েছে।
Okay, so this is 1 by beta h cut omega, and therefore q and beta is 1 by beta h cut omega whole to the power n, right? So this is what, oh, this is the end of it. Okay, so q and beta is q1 beta whole to the power n, and that is what we have written, beta h cut omega whole to the power minus n. Now you see, you could ask me one question here. The question is that in case of classical gas, what did we do? We divided by h to the power 3n, and also we divided by n factorial. Do you remember that?
হ্যাঁ স্যার।
Did not do this in this case. Yeah, so why can you tell me why didn't I take that? Hello, Mojumi?
স্যার বলছি শেষের দিকে আমি শুনতে পাইনি, মানে কি বললেন, আরেকবার বলবেন কি কোশ্চেনটা?
আমি বলছি যে when we consider the classical gas of n particles, when we consider the classical gas of n particles, then to calculate the number of microstates in the phase space volume, we divided by h to the power 3n. That is, to the power 3n because of n particles in 3 dimensions. That's fine. But also, in addition to that, we divided by n factorial.
হ্যাঁ,
Right.
ওই ইসের জন্য আইডেন্টিক্যাল আমরা ধরিনি, আমরা সব ধরেছিলাম ডিস্টিংগুইশেবল।
But in this case, we are not dividing by that. Why? That is the question that should be raised by you, right? Because you have to understand why we are not taking that n factorial here.
হ্যাঁ, সেটা বুঝতে পারছি না।
So your mind should be very curious, your mind should be curious, and at each and every point, to make it clear, you have to ask a question, relevant question, that why. You can always ask now why question can be asked anytime. But the point is, if you remember that, then you see a drastic difference here, because you did not divide by n factorial, right? Then naturally you should ask, then why we didn't do that? That is because this is I have written it here. You see, we have assumed that the oscillators are distinguishable. Generally, the atoms in a lattice where the particles are localized are treated as harmonic oscillators. Since the oscillators are localized, that is, each oscillator has definite positions, we may distinguish each oscillator. In that sense, they are distinguishable particles, and therefore, we do not divide by n factorial.
ওকে স্যার।
Okay, so again, for all of you, that here in this case, in case of classical gas, all the particles were indistinguishable, and that is why they were taken to be indistinguishable. And that is why, because these particles are moving around, some particle is at various positions, the particles are traveling in the entire in the entire phase space volume, and therefore it is difficult to distinguish which belongs to what particle, or what particle is there, what in which position, and so on. But in case of oscillators, since we generally mostly physically we deal with the oscillators which are placed at certain positions, like say one-dimensional chain lattice, then all sites are fixed, and these sites or ionic sites are oscillating about the mean positions, right? And therefore these oscillators, you can distinguish them. The first oscillator is that's that side, second oscillator is positioned at that side, and so on. So basically you can make out each oscillators with distinction, with their distinct positions, and therefore in that sense these oscillators are distinguishable, and therefore you do not divide in counting the number of states in the phase space, you do not divide by that factorial. Okay, and that's why you take qn as q1 beta to the power n, that is beta h cut omega whole to the power minus n, right? Now we have this is what I explained. I hope things are clear to you. Now you can, as usual, if you have the partition function, eventually you can get the key quantity, that is the Helmholtz free energy, in terms of this relation. Once you get the Helmholtz free energy, you can just simply calculate the chemical potential, pressure, entropy, average energy, specificate at constant volume, at constant pressure, and so all these quantities you can calculate. Okay, now these, given these quantities, or given the partition function, once you know the how to calculate the partition function classically, of course, here you have done it classically, right? Because you have adopted phase space, and you have considered p square by 2m Hamiltonian and so on. So using those, because the classical oscillator, quantum oscillators are totally different, right? So these are the classical oscillators. Now you know how to calculate the single particle partition function. You know how to calculate the n particle partition function, because these oscillators are distinguishable. So don't divide by n factorial. So this is your n particle partition function. Once you know that, you can derive the Helmholtz free energy. From Helmholtz free energy, you can calculate all possible thermodynamic quantities like chemical potential, pressure, entropy, internal energy, total internal energy, and then specific heat per at constant pressure, specific heat at constant volume, and so on. Now once you have obtained that, now you can go for a quantum calculation. You can go to quantum calculation, and you can ask the question, how is it different from the classical one, and at which limit these quantum results will reflect or produce the classical results. Those are the questions you can ask, and and probably in the next class I'll talk about that. And also, given the, as I said earlier also, given the partition function, you can put it in the form of a Laplace transform. You can do the inverse Laplace transform, and you can really calculate the density of states for the system. When you are talking about the classical one, similarly, you take the classical partition function, and then you can do the inverse Laplace transform and get the density of states for classical oscillator. Do this calculation by yourself. Okay, take this. You know that Qn beta is known. That is 1 by h cut beta h cut omega to the power n, and that can be written as like this, because this is the definition of your partition function. And from there, you do this integration. We have done it in the second sem, and also last time we used this one for classical gas. Then you take the residues of this, you do find the residues of this, and then put it here. I have done it here. Just go through these calculations, do it by yourself, and you will see the density of states is for E greater than 0. It takes this form. I think this is what I did in second semester also, the same calculation, and it is 0 for when E less than 0. Okay. Now, taking this expression, we may calculate the entropy of the system and check if it agrees with the earlier calculation, because we have done the entropy calculation from the partition function, and here given the partition function, we have calculate the density of states. And in the microcanonical ensemble, how to relate the entropy with the density of states like this. And therefore you can calculate the density. From the density of states, you can calculate the entropy of the system, and now you can match, or you can compare with the result that you obtained earlier. This is the entropy. You see, these two results are similar, same. Okay, so everything is consistent from one end to another so far, right? So with this entropy and also energy nkt, okay, this is also because even in equipartition theorem, that each this is n single part in one-dimensional harmonic oscillators, and each oscillator will have two quadratic term. Each quadratic term will give you kt by 2. Two quadratic term will give you kt, and therefore n oscillators nkt is the total internal energy, and that is what nkt. This is also perfectly all right? So given these things, so I stop here today. Please do the calculations by yourself once more. Whatever calculations you have done during the class is fine, and apart from that, whatever is left out, please do the calculations. And also if you are yet to go through the earlier notes, please go through. Okay, then see you in the next class. Okay, all right. That's it. Okay.
Okay, sir.
Okay.